all up here looks like basically converting and whatnot. And then all of this looks like Boolean algebra and switching and whatnot. Y'all having more of an issue in one particular area versus the other, or it's where it always is. Hex, all this stuff you can figure out. So y'all want us to concentrate more down here? All right, that sounds like a plan.
Oh yeah, I have one question though about the overflow. I'm
Yeah.
having trouble with
Overflow? Okay, we can take a look at that. Any particular question?
It's just that I noticed that when you like add two numbers up and at the end digits of the two numbers, if they're like 1, 1, and you get 0, you get an overflow. 1, 1, and you get 1, it's not overflow. It's the same thing with the 0. If you get 0, 0, and a 1, it's an overflow. 0, 0, and now 1, and a 0, it's not an overflow.
Okay,
I'm just having difficulty with that.
fair enough. That is 1, 7, right? Yeah. Okay. So we can look at that. I think there's a couple there. So we can go over maybe the harder one. That way we're not doing them all. Does that sound alright?
Yep.
Alright, so this is 1.7b.
All right, so your question is on overflow. So how exactly does it work, and what are we trying to do when we're calculating it or deciding whether or not we have overflowed or not? So you guys ever know how to convert to binary, right? I'm not going to confuse anybody. Okay, cool. So this is my preferred method of doing it. 16, yeah, 32. All right, so for this question, we are restricted to using word lengths of 6 bits, and that includes the sign bit. So we've got the first bit, of course, is going to be our sign bit, and the last 5 are going to be our actual numbers, right? So first, we're going to convert both of these guys to binary. That's our first step in basically all of these addition problems, is converting these numbers to binary. So what's 32 in binary? 1, 2, 3, 4, let's see, 1, 2, 5, yeah, okay, 6 bits. All right, so that's 32 in binary. But we're dealing with negative 32, so we have to do the 2's complement, right? So first step in 2's complement, exactly. So 2 complement, sorry, my handwriting is step 1. So invert all these bits, so you get 0, 1, 1, 1, right? And then add 1. So you get, easy enough, right? Just to point that out. Yeah.
Because you did the second complement because the question is asking you to do that, right? Or
So I'm doing the 2's complement because I have to represent negative 32 in a 6-bit signed form.
okay.
So to represent negative numbers in binary, first we write out the actual number in binary, and then we take the 2's complement of that number, which is flipping the bits and adding 1. And this is our result. So this is equal to negative 32. Understood? Because that's what we're trying to add. So this is one number that we're going to be adding in binary. Now, what's this second number, right? It's 14. So to get 14, that's going to be 1. Yes. Right? So then using the same process here, we're going to flip the bits. So it's 1, 1. So here's 32.
No. That's 15. That's 15. At the very end, it should be 0.
Oh, okay. Yeah. Thank you. Got it. So that should be 1, 1, 0, 0, 0, 1. So that's 14. 2's complement. And then add 1, right? So it's 1, 1, 0, 0, 1, 0. Equals negative 14. Cool? Now, finally, we can add these two. So you have 1, 2, 3, 4, 5. 1, 1, 2, 2, 1. So everyone's following me up to this step. Cool. So 0, 1, 0, 0, 0, and now this is the problem you were discussing, yes, is 0, you have a carryover 1, and that guy ended up there, right?
Yes, so you can.
Sorry.
From that you can
Oh, yes. Sorry.
Yes.
All right. So now your question is what exactly does this mean, and why is this overflow versus other addition subtractions where that wouldn't be considered overflow, right? So this is considered overflow. So if we take a look at the original numbers, we have 14 minus 32. So that's actually going to be, of course, a smaller number.
Negative 14.
Yeah, negative 14. Yeah, negative 14 minus 32. So that's, of course, going to be a smaller number, right? But that is, that's going to be outside of the range for these 5 bits, right? So if we, oh yeah, sorry, 6 bits. So if we converted this to a decimal number, let's do that. So that's 1, 2, plus 8 equals 10, right? Just converting that back because that's 1, 2, 4, 8. Yes, you're right. I was off by 1. 2 plus 16 equals 18. That's definitely not the sum of these two. So that's how we know we overflowed. We cannot represent this number in 6 bits.
Need 7.
We'd need 7. So that's why we overflowed. Now there are other numbers or other addition and subtraction. So if we just changed one of these to 14 minus 32, now we would be within the range. So if we went through that math, we still might end up with this extra bit, but if we converted these lower bits and got the same number, the actual decimal math that we could do, right? Then you would see, okay, hey, this number is in the range, and therefore we know we didn't overflow. That's the difference.
Oh, okay, I get.
So you kind of have to go back to your original decimal math to sort of check that.
Okay, I get you what you're saying. So you're saying that if those binary numbers that I got,
Mhm.
and I get the number that's the same number as the resulting number, even if I have an extra 1, I delete that extra 1 and just keep with those binary.
Mhm.
Okay.
This is basically like a signal to say, hey, I need to go back and check this.
Okay, that makes sense.
Is everyone clear?
So this one does have overflow.
Yeah, this one does have overflow, absolutely.
Because it's represented by 7 bits. And the problem limited us to 6.
Mhm. Cool.
But the answer will be 7 bits, right?
Yeah, the answer, if you were to actually do this in a computer, it would be in 7 bits. Or if you only had a 6-bit computer, good luck, first of all. And second of all, you'd get an error. You would get this right here, but the answer would be wrong. Your computer would be wrong.
Okay.
Cool. Alrighty. So let's see here. So is everyone good on converting to hex, octal?
Base 4, base 3, base whatever.
Mm-hmm.
Kind of get all of that.
Mm-hmm.
So then we'll move on to chapter 2 material more. Concentrate on that a little bit more. So I know 2.2 says represent circuit using switches, and it looks like I wrote that number 10 has the same request. So we will do 2.10. All right. This is the
Okay, cool. So we are doing chapter 2, problem 10. So, guys, if you don't have your book, or if you do, You can take a picture of that. And which one do you want to do? Start with A?
Yeah, I can do A.
Okay, cool. I'll let you write it because I'm pretty sure your handwriting's better than mine.
That's a stretch. Okay. So this one's pretty straightforward. This is a basic theorem type question. You've got two of the same value here, and then a complement as well, right here, complement of itself. So if you drew this out in switches, you've got an AND, right? And this is going to be your X, and this is going to be your Y here. And then you got another one down here. We're just going to draw it separately so you can see what's going on. And this is some output F. Okay, so if I have X, these two are both the same, whether it's 1, 0, on, off, however you want to think about it. And these two are complemented, that's also a Y. So one path, in this case, is flipped of itself. Alright, so essentially you can get rid of the Y. Because if I decide to turn X on, right, I'm going to get two switches like that, and it goes through at least one side. No matter what, you get whatever value X was. So this becomes X, and all you've got is this little X switch here. Ignore that line. And if you look up the Boolean algebra theorem, I don't even think it has a name because it's considered one of the main ones. If you have some input ANDed with another, or the same input ANDed with its complement, get rid of the two that are alternating that complement number. It goes away.
I guess it's distributing
Yes, of the Y's complement itself. Yeah, you can also look at it as X goes through, and then the basic property of Y or Y naught is no matter what, one of them equals 1, and so it's an OR. You can look at it that way. This is sort of the switch. I'm not a great circuit artist, but the idea is that you can see at some point this one will be closed or open, and it's just what X equals. Any questions before we move on to the next one? No? You can do whichever one you want to do.
We are turn 1 on.
Yeah,
Is
this
the
is
light?
a 210D.
That's a little better.
Just turn off the middle way. Get rid of that. Oh yeah, this room's high tech. There you go. Can everyone see a little bit better? Not so washed out? All right. All right, we're going to try 210D here. Cool. So this is the equation we're trying to represent. So this is the result we're trying to get, and here are two equations. Did you have a question? No.
I was going to say, isn't it the same thing as the first one? Because all you do is A plus B equals to X, and then C equals Y, and X plus Y prime.
Yeah.
Yes.
That is true. Good observation.
So, you volunteering to go out there and teach?
If you wanted to, again, you could do the distributive out and find that that is still the case. But you could also make A and B some other variable, just like you would do in calculus.
Shows that longer doesn't mean necessarily larger.
Yeah, very true. Good point. I want to point that out, is that just because they're represented this way doesn't mean you can't rewrite the problem. So as you were saying, you can write this as just call D And so then you can see it's the exact same thing as you pointed out. But that's something to keep in mind when you're doing these Boolean algebra equations, is that you can rewrite it any way you like, and as long as you keep staying consistent and resubstitute when you're done, should make a lot of the more complex operations easier to look at. All right, so since we've gone ahead and you guys are good on switches, then I assume.
Yeah, I see how you do that. How would you illustrate it?
How would you illustrate this one?
Paul was asking how do you illustrate it in terms of circuits of switching.
Oh, okay. So, absolutely. So basically, every one of these terms is going to become a switch. So we can see that, and the or plus sign is going to be switches in parallel. So we'll have, that's that first. And then the next switch is, oops, ignore that line, C.
You got the other gate though.
Yeah. All right, and so that would be this first section here. And then this next section is going to be A, B, and then as well as C again, but C not. So, made the same mistake too. And then on the other side of the equal sign, you'll just have these two gates, or these two switches.
Is there any reason that, because is there any reason for you to make a bit on or off, or is this just a choice?
It's just a choice. So I'm just labeling them. So you could, as he did in the previous problem, label the C, C naught. So if you draw C this way, then you can draw C closed on the other one to represent C naught to help make it a little bit more clear. But other than that, it's just on or off is your choice.
You want to say that's done for 2 days?
So everyone good on switches? Cool. So let's move on to Boolean algebra. 211? All right. So we'll put it back on. So what are we doing to
All right. So the first theorem we're going to use here is De Morgan's law. So essentially what that means is we can take these two like terms and combine them and get something else, right? I mean, every time. So these two like terms, right, assuming they're the same variable, and we see that it's A or B, or A and B or B, right? So we can reduce that a little bit, and we can see that, sorry, okay. We're going to go to here. We'll label it over here, De Morgan's. And we're going to start off with, let's just do this. This is a different problem, isn't it?
Step 2.
Yeah, that's A, that's B.
Oh, are they solving A and then step 1?
Well, these aren't the same problems. What problem is this? Oh, this is still problem 210, that's why. There we go. Whoops. Okay, ignore this. I named it wrong. We're going to do a little bit of rearranging first. I used the wrong name for the theorem. First, we're going to do essentially moving this one over and then bringing the A to the end so you can see what's going on. Or B. Okay, so now we can see that this right here is the same as this right here. It's just ANDed with this on this side, right? Okay, so we're going to label this x, and then filling it out, we got x or xa. Okay? Now, if we say that y is equal to a, which is how you would see the theorem in the book, we can see that this is again just a simplification theorem. We're going to get that the whole thing ends up equaling x. And that's because no matter what x equals, we're going to get some value. If a is 0, we're still getting this x is 1. If a is 1, we're still getting x is 1. And then if you flip it around, if x is 0, all the way through it's going to stay 0, no matter what you do to a. Okay? So walking back through it, we labeled these two as the same, made them a single variable, and then reduced from there. Your biggest thing when doing Boolean algebra is finding things that can be the same and then reducing them, even when they're out really, really long. Like there's one that we're not going to do directly right here. You can see that this A naught or B or C, or A or B naught or C ANDed together, this one is the same as that one, right? So this is x, it's x and x naught. One of them's always going to be 0. So it just goes straight to 0. If you didn't see that right away, you could go ahead and distribute this all the way out and then go backwards. But this is this law right here changes these to what? Does anyone know? If you have this complement here and you've got 3 in a row, like ors, what does it do? Yeah, it turns them to ands, and then it complements each one.
Sorry, trying to record it.
Okay, so any questions on that problem before we move on to the next one? Awesome. Which one do you want to do? You gonna go straight to that? That's fine. The rest of the problems on 211 all deal with finding something similar like this and reducing it out using a single variable. So if you're going to practice for the quiz, do those and see if you can find what's common between each one. And then it's almost exclusively simplification theorems.
2.13? Okay. And number 8, I heard?
13A. Okay.
13A. Okay.
I guess we can have a book. We don't have to search another page. Ignore me. That's fine.
All right. So 2.13A. All right. Trust me, as soon as you say something.
Oh, okay. So we're doing more algebra. Just
Yeah.
Deriving it.
oh, he's counting.
Hmm?
Brian's in the back counting, waving his hands around. Keep doing you, Brian. Keep doing you. I didn't expect anything less.
Cool.
I always hated drawing these out.
Alrighty. So this is 2.13a. So the first thing you're going to want to do when you start analyzing these problems is what are your inputs, what are your outputs, right? So when we're done with this problem, we should have something in the form of f1 is equal to some function of a and b, right? These two inputs. Now, of course, this function is going to be a Boolean function. So how do we start actually looking at what that Boolean function is going to look like? So the best thing to do is to just follow along with the signal. So A is some signal that we're inputting into these gates. So first we have A here and A here. Well, the first gate we hit is a NOT gate.
So it inverts into A.
Exactly. So here, if we were to put a multimeter and pick it off of that line, we get A prime. and A is right here, right? So what's A and A prime? Exactly. So this should always be 0. Okay? Now we're following B along. So B comes here, here, and here. So what's 0 or B? B. What's B or B? B. B or B? So the simple form of F1 should just be B. How do we write the more complex form? Well, we're going to just start again over here. What's the first thing that happens? A gets complemented, right? So the first operation we do is A complement. What's the next thing? Dot A. That is ORed with B. And then we end up here. So now, once we're almost at F1, we're going to come back a little bit. What's over here? That's ORed B or B. So B or B ORed with this gets us the longer form of F1. Does that make sense? You can do a little bit. Say again?
You have to draw your final answer.
Oh, draw my final answer? Yeah. Yeah.
How are you going to draw?
It's just gonna be a lot, right?
Yeah.
Just like this?
Yeah, that's just like that. So if this were more complicated, you would again, following this kind of rule going backwards, you would draw that circuit again. And I'll do another
What
one.
does it mean?
B, so that means F1 is equal to B. So your output is the same as the input of B. So that's all you have to draw, is B, a line, and your thing. That is the circuit. Yes?
Right. I'm just wondering, should we put parentheses around the A complement dot A plus B? So the whole thing should be in parentheses? Or it's not
Yes,
necessary?
but because they're in order, you don't need it.
Oh, okay.
It's kind of like if I had x plus y plus z, and then did it again later, but they're all already in the front, doesn't matter.
Oh, okay.
But that would be how you would label the gate, and then you can see that you get rid of it.
Yeah. Cool. I will do a bit more complicated, a later problem later in the chapter. I won't say it's more complicated. Hmm? So I'll start with 226. Find F, G, and H, and then simplify. 226 is what I'll be doing. What's the B? 226B. So we have input A. Yeah. I just love making it easier for myself, right?
Don't choose the easy way.
Mm-hmm. Or, not, and.
No, you're good. You're good.
Okay.
It's just very complicated. Anybody get up at 4 a.m. and watch the opening ceremonies?
I did not.
No, I didn't either.
Does Dr. Russell teach electronics one in the summer?
He did. If they hold it again, probably, but it's not guaranteed if they're gonna hold it.
When I took it over the summer, Lobby did it. So he was actually better. He was actually better in the summer because there was a smaller class and you got more of one-on-one, and the class kind of directed him. Well, I mean, eventually you're gonna hit that point, and you're gonna have to take it, or else you're gonna stop your degree. So.
Did someone have a question?
Someone said question. No? Okay.
No? Okay.
If you've taken him for foundations, he's better at electronics than foundations.
Yeah.
If that's your concern.
Well, he's a technically, I believe, a physics PhD major. So the physics behind. No, I'm saying that his PhD was on the physics behind the electronics diodes and MOSFETs and transistors and all that. So yeah. And therefore his electronics is his forte, is what I'm saying. That's it.
I just heard physics, that's why I was
You didn't let me finish.
Looks good to me.
All right. So this is the problem we're trying to do. So again, just starting at the very beginning and moving forward. So we'll write the equation, then we'll figure out what the output is, and then we'll write the circuit for the output. Cool. Let's see here. So first we have A and B. So this is A and B, right? Coming on to this side, we have A, B, not. Very important. So, coming to this gate here, we have B again, C, B or C. Then we come to this AND. A and B not, or B or C. Oh, sorry. No, not here.
Shouldn't that be a dot? A dot, B dot, B plus C.
Oh, yes, you're right. Apologies. That should be a dot, yes. Yeah. So it's A and B not, and, for this and, B or C.
No, it's actually
Cool? Now, so that's for that line. Coming on to this line, you have A, B prime, B or C. And then I'm going to do a larger bracket, prime. And then finally, we have a final AND with C. So F is so that is our final equation for this circuit.
And you can go further. Yep. So you got it. So right here, this A B naught right here, can go to A naught or B naught.
Okay, and then you can start
Yeah, you
simplifying.
can go down here and go further.
Okay, cool.
So
So-
just change that around and it'll work. So change it to A naught or B naught.
Cool. All right. So now we're going to start the simplification, right? So A naught. So applying De Morgan's to this guy. Right? And then moving this guy in.
Yeah. Just make up the minutes ending on the magical thing, apparently.
Thanks, man.
Right? So, of course, this guy goes to 0. And 0 or anything else is just the other thing. Let's see. And then A prime. So then we can factor out the
Okay, go. You're doing.
A prime.
Okay.
Okay.
Try applying the words to that.
To this guy? Yeah. Okay, makes sense. So then, here's where I'm going to try and apply a little bit of trickery, right? So we have this factor here, we'll call D. And this factor here, we'll call E. D and E. Right? So we're just going to do a straight substitution. We have D or E prime times C. Or not times, and C. Keep my language straight.
So we'll look like that. Multiplied. Complement.
So then we can again apply De Morgan's law here. D prime. Oh, sorry. Not.
No, you're good. Okay, yeah.
Yeah. And
And
E prime and C. Well, what is D prime? I'll do it off to the side here. Since D equals this, D prime is going to equal prime
you need to find out B or C. Oh, okay, I see what you're doing. You're good.
Yeah. So then this should go to A double prime, B or C prime. Make sense? And E prime is going to be B, C.
The Morgan's law again over there?
Yeah, I used De Morgan's law here. Sorry.
I mean the D.
Yes.
No, I just moved this guy in here. In
Their
here.
hands.
Yeah, so since this factor is ANDed with this factor, you can distribute this not symbol. So you have A double not, but that's just A. So your final thing is A, B, C. So I have it. You can use the Morgan's law here. Okay. So you can use the Morgan's law here, but I haven't gotten to that point yet.
Oh, okay.
So we probably will, but we'll see. All right. Keep it a mystery. And again, I'm going to distribute the not. B double prime C prime, which is equal to B C prime.
You don't apply De Morgan here?
Say again?
You don't have to apply here De Morgan for dot B dot C, no?
You can.
You,
I've yet to see if I need to. Yes.
the rule is the rule.
Yes.
You have B naught and C, and then you have the complement of that. When you apply De Morgan's law, does it not become B or C naught? Because you have to not the or. Next line down.
Next line down.
Yeah. So when you apply De Morgan's law there, should it not be an or?
Yeah, it's
You're
not
not
like
in the
a
and.
So right here, he just distributed,
Next line down.
right? And then here, he was just saying that the double A is an A. He hasn't actually done the De Morgan's law. He was distributing the complement.
Yeah, so let me be clear, I guess. So right here we had
Make that
D
double
prime.
knot clearer.
Yeah.
That's my question.
Mhm.
Because, I mean, I thought that if you want to get, like, put the knot of all of them, you have to use the Morgan's law to do it.
Not necessarily when you're dealing with or. If this were or here, then yes. But since this is anded, you don't have to. You just distribute it.
But we have two
This section, yes. But this A does not have to be De Morgan's. Yeah, because it's outside the bracket.
Yeah, but the whole thing is with a knot.
Yeah, the whole thing is with a knot, yes.
So shouldn't it be like A knot plus B plus C all knot? That's what
That's your question, okay.
I mean, if you just start back over and do this right here originally, instead of trying to toe it off, you get that right away, and it goes in 4 steps.
Okay.
This right here between the A and the parentheses, that turns to a plus, right?
Oh, okay. Is there another form that I'm missing? So there's
This right here is De Morgan's law, so you can break it apart like that.
Okay.
That is what they're saying. I think that's what they
Okay,
probably want to do.
so right here, when you're knotting this,
Yeah.
okay, and you're distributing this knot into here, you have a dot right there. Okay,
That
so when you knot that dot, it should become a plus, should it not?
Yes.
Okay.
Okay, that was the question.
That was what I was missing. Okay.
Yes.
And so then you're also saying that applies here too?
Yes.
Okay.
Crosses out my right.
Yeah.
Just next to it. Just so that we're extra clear.
Yeah. A prime. Yes. Or B. C. Okay. Prime.
So the only thing that you did that they did is you didn't distribute the C right away.
Oh, okay. So that probably helped cancel some stuff.
Well, so the C will get rid of some zeros. So if you go back there, you should be okay.
Okay. So should be. Okay. So
rewrite
once.
that out, I guess.
Okay. So then.
Good, now it's going to be
Yeah. So just
Yeah.
double knot.
redefine what D and E are,
Yeah.
or rewrite what D and E are.
A prime, prime, or B or C prime.
Yeah.
Yeah, okay. Same thing with this guy. So B prime, C prime, and then say B double prime or C prime. B or C. Okay.
There you go.
Okay.
And then you can rewrite the A here.
Yeah. All right. Sorry.
Nope, you're good.
C prime. Okay.
Is that better?
Sorry.
Nope, we're good.
Alrighty.
It's been a while for us. Sorry, guys.
It's okay, Taylor.
All right. So substituting these guys back into here. All right. We have A or B plus C prime, and with this guy, so that should be B or C prime and C.
Yeah. So don't forget to put the A as part of the A.
Yeah, that's right.
There you go.
So, yeah. So now let's distribute in the C to all of these guys. So distributing in here, we have AC plus or B or C prime C. All of that anded with BC or C prime C.
Okay.
Again, canceling this out to be 0. We have BC, AC, and then using De Morgan's law one final time on this guy, we have B prime, C prime, sorry, no, and C. BC. And finally, so this guy comes to 0. So B not and 0 is 0. So you finally end up with, and so then AC or 0 is AC. So you end up with AC and BC. And since the C is redundant, you end up with A, B, C's.
Woo.
So walking back through that, since we had did you have a question real quick? Walking back through that, since we kind of diverted a little bit, starting up here was directly from the circuit, right? Okay. So the next step he took was to split up this A and B using De Morgan's, right? Okay. Then we saw through distributing out these two that B not B's goes to 0. Okay. And again, we break down, find something that it's in common, and we're making something easy for ourselves. We got D or E in the not. So we distribute that out and make ourselves reverse De Morgan's, right? Well, I guess it's still technically De Morgan's, but it's, and then we and that together with C. Rewrite it back out so we can see it. And we've got our D back here, our E, and our C, right? Okay. So then he distributed the C out individually to these, the C here and the C here, to get rid of this C naught, or these two C's.
So he multiplied the C in?
Yeah, so he brought this out to this one and to this one.
I thought only he multiplied only put to one of them.
Oh, no, you're right. It's only right here. That's my bad. It is just right here.
Okay, and so where did he get the C there?
Oh, he multiplied it twice.
Okay, you don't actually. So the redundant C at the very end is unnecessary. You don't need this.
Alright, then A, C.
Yeah, oh, I erased the wrong one. Leave this one in, okay? So we'll take this and we'll make this just,
Yeah.
okay? So then we come over here and this A, C, or B, right, goes to 0, which this is ANDed, so it gets rid of this, right? And then you again have A, C, and BC. C is redundant.
B plus C, right?
B plus C.
Yeah, at that point you still have the B plus C.
B plus C prime.
Oh, and then you can.
No, you're distributing to all of them. He was right.
No, because if you distribute here, you got two C's.
From here, and then that goes in here. There's that, and that goes in here. There's that. It's parentheses.
Yeah, but you can't distribute to all of them, otherwise you'd be multiplying by X squared.
Well, isn't it? It's C ANDed with this term and ANDed with this term. So you should be able to distribute to all.
It's because it's got the plus here.
Oh, okay, I see what you're saying. Okay, so to this C, which, I mean, you can't really do it to both then because you're doing it twice.
Got B plus C.
Maybe easier just to rewrite it because we've written it so many times.
Yeah.
All right, since we've rewritten it so many times, we're just going to redo it. Should be 5 steps. He's not incorrect, but there's a lot of writing down there.
Yeah.
Okay, so 120. What are you?
Is it 121?
I have no idea of the number, but I have the question.
120.
It's the same thing as 121.
There we go. That's division. Do you want to do it?
never seen this before. What the hell?
Is that just remainder? I bet you that's remainder. That's a way
this
of
is
writing it.
Yeah, this must be the number here. And then there you are.
Oh, this is what's supposed to go on top. It's just shifted over to the side. It goes in one time
Oh, I see.
to that whole thing. Yeah, that's what it is.
Interesting.
That's a weird way of writing it. I'm not a fan of it, but it technically works. I mean, might as well just go for it.
Yeah.
Yeah, that looks right. Okay, this is the binary division problem we're going to do real quick. The method is very similar to regular long division. You kind of treat them like decimal. They're not actually decimal, obviously. So we're going to go ahead and put the 110 and then 100011101. Okay, well, too far out. That's fine. So 110 cannot fit into 1001, right? So you move on to the next one. It can fit into 1000. How many times? I mean, it's binary, so there's only two options, 0 or 1, right? 1. So you put the 1 right above where you're at, and you bring it down. 110. Draw your line, and then it's back to subtraction. So if we bring this down, doing regular binary subtraction, you get down here and you're going to have 0, 1 with all your borrowing, but I don't want to mark up the paper too much, so makes sense? Okay, cool. And then you bring down this one, but it doesn't quite fit, right? You can't fit that in there, so you write a 0 up here, and you bring down another one. Okay, right? Okay, so now it fits again, 4 digits, 0 or 1, fits in once. Nope, yeah, it's right here. Okay, so you write that one more time, bring the line across, and doing more subtraction, excuse me, you get 1, 0, 1, right? Bring this guy down again, all the way down. Okay, now it fits in again one time. This makes it pretty easy. It either fits in 0 or 1, right? Okay, so bring it down. You got 1, 1, 0. Draw the line again. Doing subtraction, you're going to get 0, 0, 1. Right? Because this is like a 2 and that's a 1. All right. Bring down the 1 one more time. Okay. Fits in one time. 1, 1, 0. Right? Do the subtraction, you're going to get 1, and this is 8 minus what? 1, 1 is 4. No, it's 3. 3. So 1. So this up here is your final answer.
That's the quotient, right?
Yeah.
Yeah. So since there is a remainder, this 1, 1 right here, but remember in binary you don't have decimals directly. So you bring this back up and you're going to get, here's your whole number value, your integer, and then it's like a remainder 1, 1. So I can't go any further out here, right? Because it doesn't exist. That's behind the decimal. This is integer division. So you have this remainder right there.
That makes it work. Thank you.
Yeah, so if you think about doing all this division, it's go back to first and second grade math where there's none of that decimal. All right? Just stick with the whole number. Because the remainders actually mean stuff in binary math. It's not just more decimal to it. Right? That's not in this case, but that's where you would have like overflow type stuff. And then when you're going between hex and octal and octal, that's where those come from as well.
Can you guys go to what the consensus theorem? I just didn't get that.
The consensus theorem?
Yeah. I was having hard to understand the theorem.
What chapter is it? Problem 1?
Chapter 2.
Chapter 2?
Yeah, it's Boolean algebra.
Yeah, it's Boolean
Okay.
algebra.
It should be the last section.
xy plus yz plus x prime z equals to xy plus x prime z. Is that theorem?
Yeah, we're just trying to find what page it's on here.
Should be the last section.
Yeah, it is, but it doesn't directly say it, so we're trying to find
It's
the
at the
page.
top of the page on the right.
Of course he knows exactly where it's at. Top of the last section, top of the page on the right.
I know this is the theorem right here. This is the consensus theorem, but I still didn't understand how it works.
Okay. Yeah, we can take a look at that. We're gonna find the page so we don't say the wrong words. Oh, here we go. Consensus theorem right there.
Go find it?
Yeah, we did.
Good.
We thought it was like a section title.
Oh, no.
Okay, so make sure I don't screw this up. Now that that's on video. All right, so it's
XY or YZ or X prime Z is equal to XY or X prime Z.
bring that out.
Yeah, or factor out the,
Yeah, because this, yeah, fight that out. That's my best guess. Okay, so without doing any sort of crazy stuff, we're just going to go straight algebra and do like reverse stuff. Okay, so we see that this is in common, right? So we got x or z, y, right? Or x prime z, right? So it's still equal to this.
and then we can,
What am I missing? I'm missing something here. Can you... Is this the complement of something else using De Morgan's?
no, you'd need a knot out here if you wanted to do that.
All right. You could probably do this though and get x or z. No, it's x or z prime.
Yeah, if you wanted to do any kind of De Morgan's, you'd have to have the knot on both of them.
Yeah.
So,
So specifically, what is your question? Like, how does it work, or?
You know, how did it go from there to there? I just
Okay.
want to see the transformation. That's the
maybe distribute.
It's not helpful at all.
The consensus term. No, that.
That's not helpful. It's redundant. Oh, okay. So it's just redundant.
Yeah.
Okay. Okay, so if you look, the reason this is called the consensus theorem is because this item right here is known as the consensus term. It's a redundant term. So if we were to, let's see if we can see it by drawing out the circuit.
I know it's going to be partial or total, but I don't know how to get the actual.
Oh, there's electronics.
All this goes together.
X prime on the bottom.
Oh. It's going to be a really big or. That's fine. Okay. And that all comes out and it equals this one over here. Okay, so here, x and y. If, let's try it out, because this is more like a try and see. If we say y is 0, right, that means this one right here is 0, and so is that one, right? So all we're left with is x prime z, okay? Now, if we say, assuming that x is 1 here, this would make 0 anyway, so that would come to 0 as well. So we'll say x is 0. So that makes z and x, right, go to 1. Now, if we say y is 1, okay, we've got if everything is 1, now we got y is 1 and y is 1. Okay, so then if this comes out and you get 1, now my pen's not working, and we get this becomes 0, and it's just this one with z still involved. Okay, so
Basically add 1 to the YZ term.
oh, okay. Okay, so if we continue to do this, right, we see that this term right here doesn't matter. It's just going to be whatever these equal. Okay, and so if we do math, we'll do the math reason now. So the idea is that this one right here, no matter what it equals, whether it's 0 or 1, these will take over.
That's gonna go with the whole.
Yeah, so that's the idea. So if we go back up here, we're going to use the idea that we talked about earlier of multiplying by 1. Okay, so we're going to get x, y. What did I do?
Y, XZ plus.
Oh, okay, got it. And I can do this because this is 1, right? Okay. So now, next step, we're going to go ahead and bring this stuff down so it equals x, y, or x prime z, okay? Or x, y, z, and my pen is dying again, or x prime y, z, right? All right. So now we can combine those, like, or bracket them off, parenthesis, whatever you want to call it, and we're going to get x, y, or x, y, z, or this whole thing, x prime z, yeah, or x prime y, z. Okay? Make sense so far? Awesome. Now we can break that out, and you're going to get x, y, 1 or z. Do you see how we did that? Okay, cool. Back over here, same process. Although I must mess that part up, but we'll go back here. X or z, right? All right. So these will always be 1, right? You're left with x, y, or x, z. You're probably not going to be asked to prove this one, but the circuit-wise, what's important is that this one, depending on if you went ahead and did all the possible combinations, you will see this will not matter. Have you guys talked about K-maps yet? You're working on them? Okay. So if you want to, K-maps are an excellent proof of all of these theorems. You can go ahead and do that because it's much simpler than writing all the combinations, and you'll see that y and z comes right out. No matter what you do to those, or that and, it goes as 1. It's 0 or 1. Those are the only two options, right? So if this one's 1, or if this one's 1, that one doesn't matter. And based on these two, since this one is opposite, right, x and 1, one of them will always be opposite of the other, or they're both 0. Like, you're going to get 1 or 0. Right? Okay. I know it's a little weird. It is a theorem, so some genius back in the day came up with it. Not us.
Thanks.